is here in this class is mostly we begin with the position vector function, right? So if you write down sigma t, that comes with a component ft that is multiplied to the I vector, and gt, that's calculus 1 function, that is multiplied to the j vector, and ht multiplied to k vector, right? So the whole thing is a vector. It's indicating position, relative position from 0, 0, 0, right? One more thing. So we talked about component function, and this is might be a bit of challenge, but not so much. Maybe some of you find it's very natural. I will only make part B an exercise. So we have vector u and vector v and vector w. 3 vectors are given, and v and w are perpendicular to each other and have the same length, hovering in 3-dimensional space. And we're going to consider the following vector function. U, there's no t part multiplied, right? So it's just fixed. And v is multiplied by cosine t, so I would rather write like this in part A. Sigma t, I'll try to keep writing like this. Cosine t first and then v, because we usually write scalar in front of the vector, right? We don't write v times 2, you usually write 2 times v. So that's cosine t is a scalar, correct? Make sense? And then write sine t multiplied to w vector. Right? Try to give a meaning to that. So this u never changes, is kind of a position vector. And here, let's say this is 3D picture, right? Understand this is a 3D picture. This is 0, 0, 0, 0. This is u vector, right? And there's a v vector added kind of to that, cosine v. But let me first look at v vector here, v, displacement vector, u plus v, right? Okay. Rather than going from here to w, it turns out it's better to put w here, but they're perpendicular to each other, right? V and w. So I will put something like this. That's the w, and they're perpendicular to each other, right? Those are the 3 vectors. If you put it like this, we can interpret the meaning of this one. All right. So as t varies, nothing happened to u, but v is usually it's a shrunk, right? Shrink to, because the cosine t is magnitude is usually less than 1. So let's see where this point is when t equals 0. When t equals 0, what happened to the cosine t? 1, right? How about w? 0. So we're here. That's the position from u plus v. Do you agree? U plus v times 1 and 0 vector. So that one as a position vector is indicating this position right there. That one position, t equals 0. Fair enough? How about t equals pi over 2? You see where that goes? Pi over 2, make that one 0. Pi over 2. Cosine is 0, right? So sigma pi over 2 would be u is still there. Now this vector is a 0 vector. How about the next one? That's 1 times w, right? So u plus w would be here, correct? Okay. So let's check in the middle what happens pi over 2. Then sigma of a pi over 2 is u vector there. And what is cosine pi over 2? I think it's roughly 0.7. That's 1 over root 2, right? Cosine pi over 4, I'm sorry. This is supposed to be pi over 4. What am I doing? 45 degree. So 45 degrees is 1 over square root of 2. It's roughly 0.7. So roughly that's a 0.7 v plus on sine pi over 4, 45 degree again, roughly 0.7 w, right? So 0.7 is roughly here. This is 0.5, right? Half of v. 0.7 is roughly here. Agree? W, 0.7 is roughly here. So parallelogram, but because their angles are 90, this is rectangle, right? So they're here. You try pi over 3 and pi over 6, then what's going to happen? It's done from here. Should believe that? because their relationship is exactly like ij, right? I is length 1, j is length 1, has the same length, and they're perpendicular to each other. So you know what happened if I do cosine I plus sine tj. You know that's a circle, right? But it's like, take that copy and flip it around and embed it somewhere in the space. Then length and that length being the same, so it's like a scaled version of this phenomenal thing. So would you believe that it's after that much of understanding, it's exactly the circle going around this vector v and w with radius what? Yeah, that's that. It's a length of vectors r. So here's r. It's the length of vector v and length of vector w, common value. Does that make sense? Yeah. So if you actually put this one without specific information, u and v and w, like they're given in here, type it into Mathematica, the parametric plot, or my command that I posted in the Google Drive, and it'll sketch one circle that's hovering in the space, right? That's what that's going to be. Does that make sense? These points, the component you calculate is the position vector from relative to 0, 0, 2, 0, 0, 2 that. Okay. Hope that makes sense. So let's go ahead and calculate with this example. U is given like this, and V is given like that, and W is given like that. And go ahead and check if actually the W, V and W are perpendicular to each other. If they have the same length, then our interpretation of this thing is going to be this, right? Oh, that makes sense. So that's our exercise number 1. It's a very simple exercise. You just combine this vector, the sigma t, and simplify x component, and simplify y component, and simplify z component. Right? So that's your exercise. Exercise 1, do part B. In addition, check the orthogonality, right? Are they really perpendicular to each other? And if they have same length. All right. So let's begin with this in addition part first and check first maybe. All right, was that okay? That's each component vector. If you type this one into command, whatever, MATLAB, whatever, it's going to sketch a circle hovering in the space. Any question? I think the challenging part is that if I give you this formula instead of the vector version, then you can actually go backwards and figure out what this one is by putting it into a vector form, right? All right, so that's the picture they have, the similar picture I explained it here, 0 to u. From there are two perpendicular vector in the space, and that's going to make a circle. If v and w are not relative, the perpendicular to each other, or they don't have the same length, it's going to create an ellipse. Not necessarily ellipse that is upright, but it's kind of tilted, rotated around kind of shape. But in general, if you put cosine and sine in front of it, and that's going to be an ellipse. So I chose just random two vectors here. Let me see if I have all the vectors shown up here and explain this picture. Let's use my program script there. That one vector is 1, 1, 0. The other vector is negative 1, 1, 1. Do you think they are perpendicular to each other? They are perpendicular. If you dot it, you get 0. But length is not the same. This one has length square root of 2, right? This one has length square root of 3. So one vector is a little shorter than the other like that. So if you sketch it cosine and sine, it's going to make an ellipse like that, right? But it is still perpendicular. If you lose this perpendicularity, it's going to be something like this. Then if you actually try cosine and sine and dotted it, and actually something like this version. But it is still ellipse. If you rotate around, it's a perfect ellipse shape. So if you look from above like that, and then you can see that's ellipse version in there. Right? Does this thing make sense? Question? The question? So that was a position vector, and next thing we enter is velocity vector, and after that is acceleration vector. The velocity vectors is understood like this. I think it's easy to understand. If this is a displacement vector, sigma t plus h, let's say there was at time t0, and here's the position. Here's O, and here's a vector. Okay? Next moment, let's save the t0. Next moment it's here, t0 plus h, over there. That's the position. The displacement vector would be this vector in here, right? This is beginning point, t0. After a few split seconds later, it's here. This doesn't mean it traveled like this, right? Maybe it traveled like this really quick. Who knows, right? But it is the displacement. If you measure it, if you saw it here, and next moment, and it is here, if that's the information, this is called the displacement vector, right? So, if this is really, h is very, very small, then we kind of imagine that this probably didn't happen because it's so short, time interval. It's pretty much representing how it moved if it is very, very short. So displacement vector would be sigma t0 plus h minus sigma 0, right? That would be this vector. But if you divide this one by its time interval 1 over h, which is a scalar, that's their definition of an average velocity vector. Average velocity vector. How do you enter velocity vector here? Limit h approaches 0. If this limit exists, then this one will be very, very short, right? Because this vector is almost the same if it is continuously changing its position. But h is also very small, so you enter indeterminate form, it actually becomes some significant size of a vector. So that's sigma prime t, that's their definition. Like if it is defined like this, we use this symbol. And the way it works is just like component-wise. If sigma t is given by ft, gt, ht, right? It's given by this one formula. Then what is this sigma prime t? Is simply, if you go through the definition, it's really easy to see that each component, f prime of t, g prime of t, and h prime of t, is the answer to that. So this is what happened mathematically, and they call this one derivative of a vector function, which doesn't care about what context is coming from. It's not geometry or anything. It's a pure algebraic object. You differentiate it. It's called the derivative of a vector function. But if your sigma t is a position function, and what could be the good name of this sigma prime t? Velocity vector function, right? Velocity vector function, not velocity vector. Velocity vector would be just one vector there, right? So we recognize this as a velocity vector function at each time t. So that's their formal definition out of that. But you can always tweak the question and challenge this idea in a physical sense. For example, if I'm going right like this, and if I have the sigma t, you can ask such a question that this is one position, and this is, I calculated this sigma prime t, and then it was this vector there, right? If it is a good calculation, what should be the meaning of the sigma prime t? That's the magnitude of a velocity, right? So what's a good word for that? That must be speed, right? So you can ask in a different way. What if this one, it has its own speedometer? It's like, suppose this is like a railroad. It has its own speedometer, and according to that sigma t, it moves travel along this path. It has its own speedometer. Is this reading of the speedometer actually coincide with this sigma prime of t? You can ask that kind of question, and coming from the physics. Then you have to calculate the arc length of that and all that, and you have to examine, is this idea, mathematical idea of sigma prime t representing the velocity function, if sigma t is a position function, does it really coincide with this idea of this has its own speedometer and traveling exactly following this position function? Is the reading of a speedometer is exactly this magnitude of this vector? Is absolutely non-trivial question. You actually have to calculate using this arc length and all that. It wasn't too bad, actually. You will see that it's not too bad. It actually agrees with the arc length version of the speed. So get a good sense that that might be a good one. Acceleration turns out is a lot harder to justify, but let's just stick to velocity vectors and the speed at the moment. That's the physical intuition, the interpretation of a derivative of a vector function. Geometric idea is that if you have this thing in 2D, let's say sigma is given by ft I plus gti, gtj, that's the parametric equation. You look at one position there, t equal t0, right? The position vector. And if you calculate sigma prime t0, and you will compute f prime of t0 I plus g prime of t0 j, right? That will be velocity vector. But geometrically, it creates little line segment array that happen to be what to this curve. What is the geometric word that describes the quality of intersection there? Tangency. So this creates actually tangent line, right? Okay, so you can use this direction vector to compute this tangent line. So how is this tangent line looks like, this tangent line L? Let's not write down Cartesian equation. Let's write down parametric equation, right? Right, how do we start from this position there, right? And plus t times this directional vector. Isn't that how we compute that, right? So what is this position there? That position is a sigma t0 at that, t equal t0. That's a position vector. And then you add t times velocity vector, right? What is it? Velocity vector is this is the velocity vector. This is sigma prime evaluated at t0. Does that make sense? Yeah. This is a position vector, And this tells you which direction it's going. You multiply t in front of it, and that's going to parameterize the line. And how many equations are there to parameterize a given line like that? One or two? Infinitely many. That you can multiply any number in there. You can create a different type of parameterization. Line versus motion, that's a different thing. That's what this last question means. So that's to the explanation. So they define derivative of a vector function in this way. I just explained. Yes, go ahead.
So that parameterization where it was sigma t naught plus
Uh-huh.
sigma prime t naught.
Yeah.
That sigma prime, you said that's the evaluated. That's like a number. That's not another function.
This is a vector.
Right.
Yeah.
Okay. Yeah, but it's not like it's not a function of t.
It's not a function of t. It had to be evaluated at t. That's why I'm using that t0. And it's always a good idea when you're distinguishing t versus t0. If you're thinking about one moment, always try to use a t0, t subscript rather than t. That may represent a general variable in here. So especially things like this, it's better idea to use t0 instead of t, so that I can use t right here, right? That's the whole thing. All right. So why do they call it different name? Derivative, because they take this into an abstract vector, not position vector, a velocity vector. In mathematics, there's a more abstract version of vector, and that's the term for the very general term. In our context, this is a velocity vector function. Oh, I have that sigma t up there. So why don't we go ahead and just compute this sigma prime t and sigma double prime t. I think that's simple enough. So all you have to do is just take the derivative of each component. Just practice and think about the meaning of this one later. Example 5 was this guy right here. So I'm going to grab that. I can't do this one. So this. Okay, that's your exercise. I think it's, yeah, number 2. Sigma t is a vector function given in example 5, and here is the vector function given here. And u and v and w are this. You plug it in there. If you already have that answer simplified before, right, you can use that. And compute sigma prime t and sigma double prime t. Differential 1 time, differential 2 time. Each of the components. That's what they're asking. I should have grabbed the solution rather than this one. So going back and grabbing the solution in here, that's a better one to grab. So we simplified already and worked on this. So I'm going to put it down here. And you can copy this one down. That's our version. This is our sigma t, right? Compute sigma prime t, sigma double prime t. And don't think about what it means. Just mechanically calculate this one. Exercise 2. No, was that okay? Just keep differentiating. That's what you had to do. So I'm explaining the meaning of sigma prime of t. Sigma prime of t is very easy to understand intuitively. Sigma prime of t represents the direction of its moving. That part's easy, right? So, however, this length of this vector we calculated here, does that really represent the reading of a speedometer of the moving around? And that's not easy, but it turns out it is. The magnitude of that, so magnitude of this thing, is actually the speed. Then we need a little bit of arc length idea to justify that. So it's not easy. That's what happened. Right? How about sigma double prime of t? Everybody knows the name of this one. This is named acceleration vector function. Especially this is acceleration vector, not acceleration. Alright? So if it actually spin around like this, right? With a constant angular speed, what will be the acceleration of this thing if you have an acceleration meter? I don't know the name of it. There's a speedometer. Suppose you have an acceleration meter. If it spin around at a constant angular speed, which is the situation here, what will be the reading of this acceleration? It's a zero, right? Speed is not a constant movement here. But the magnitude of this sigma double prime is not zero, is it? It's not zero. So we need different interpretation of the acceleration vector, right? It's not the same as, oh, the speed you read there in my velocity vector, the norm of that, here is different. The norm of this vector is not really representing the acceleration reading of this object. So it is Newton that interpreted that that's not the right way to think about it. This acceleration vector you created is not really the acceleration you normally think. It is pointing where the source of vector is. If you actually calculate this one, and then this one points to this direction. If you plot this vector at that position using, mathematics or something, it points to that direction. And Newton's conclusion is that this vector is pointing where the source of force is. There is a centrifugal force, or whatever is attracting toward it, that's why it's pointing around. And how much of the force is applied to that direction, that magnitude is precisely representing, this magnitude here, precisely representing the original source of the force. How much of the force is exerted along that direction? Orthogonal projection says zero, right? Therefore, no force is acting on that direction. That's why the velocity is constantly not changing at all. So that's the Newton's contribution. It's very easy to understand things are moving in a straight line. Hence, it's introduced in Calc 1, right? But if it is a three-dimensional direction, it's constantly changing direction, the meaning of the second derivative, which I'm about to go through it geometrically, doesn't directly translate to the way we understand force and acceleration. So Newton's second law of motion is actually a lot deeper than you think if you enter three-dimensional world. All right? So here is interpretation of this thing in here. So it's moving. It's mathematical, it's geometrical version of the meaning of this one. Physics, Newton's, changed the whole thing to a force in here. Before we enter that, let's understand what this sigma double prime means. Here, the sigma double prime is this. Sigma prime t0h minus sigma prime t0. These are the two velocity vectors, right? Subtract as a vector and divided by the time interval h. This one approaches what vector? Sigma double prime t0 as t approaches 0. That's mathematical definition. So here is velocity vector, sigma prime t0, correct? And here is, 1 moment later, sigma prime t0 plus h. We're about to subtract this vector from that. One of the strange things is that they have different point of application. If it is a position vector, they join same point of application. The meaning of the difference two vector was natural, the completely displacement vector. But subtracting this vector from that vector, strange, don't you think? And there comes this idea of a parallel transport. You parallel transport that vector and put it on right there. That's our sigma prime t0, right? And then you subtract, and then that factor right here is representing this one in here. And then they divide it by time h. Any careful person will raise a doubt in here. What's really going on here? I mean, moving that vector over there and subtracting? I'm not sure what the Newton thinking is actually correct. It is a reasonable question to raise it. So there's a lot of issues here. There's a lot to take, a lot of work to be done to justify this connection. If this is our definition, takes a long time to calculate it and justify it. Everything's fitting and consistent. So wave our hands and we believe them. This is the acceleration vector, and it is Newton's idea that's actually the source of the force and creates all these changes. If it is not simple as a circular motion, and it's more involved. A lot of things are multiplied and the factors are in there. If it is circular motion, it is directly related to that. And cross product also, it is in its nature, is that two numbers are multiplied and added. So it turns out it's more work to verify, but it turns out it is the situation here, mathematically, just like a product rule, right? And this is a bit harder to understand. You remember the chain rule. If I have cosine t, sine t, what is the name of this thing? It's a helix, right? Cosine and sine and rising above like that. That was a helix. So if you compose this one with, for example, t squared, then cosine of t squared in there. Here's the sine of t squared. And t squared there, right? So each of the component is composed with a further function. So how do you differentiate this one? What rule do you use? Chain rule, right? So if you do it component-wise, it turns out you have a scalar everywhere. This qt, qt, qt is the same composed part in there. They're all common parts. So you can factor it out, and the rest of the part is just differentiating cosine and sine and whatever the outer function in there. So it looks a lot like chain rule, as we know, but we don't write q prime t and as a second factor. It's a scalar factor, so we usually write in front. So these rules are not hard to understand. They make sense, right? Just pay attention to always that, is this a scalar? Is this a vector? Is this whole thing scalar, or is this a vector? Then you don't usually end up at abusing notation. All right, this is one of my favorite example that algebraically so simple that intuitively, physically or geometrically is almost impossible to understand in my level, my knowledge. All right, let's look at it. Sigma t vector such that is a constant. Can you imagine an example of a non-trivial movement has constant speed? We just looked at one, right? What's an example? Sigma t being cosine t, sine t, and 0. Or that example 5, UVW vector hovering and then rotating on the same angular speed. What is that? That's exactly constant speed, right? Well, some of us answered that. That's the situation. And they're saying the velocity vector is right. It's a velocity vector is perpendicular to the position vector, right? That's always what it says. So let's prove that. How do you write this one without absolute value? Let's start with this. Is sigma t, its length of this vector is constant c. Is that okay? There is no t in there. How do you write this one with the sum notation we have here so that we can do the derivative thing? Dot product. Thank you. So we enter dot product like this after you square it. Right? Still constant, correct? How do you write dot product of the norm of that is dot product to itself? Remember that? x1, x1 plus y1, y1. That's exactly the length. So sigma t times the sigma t, right? C squared. That's the equivalent condition we have in there. And they wanted to know about sigma prime t. And here's one equation we know. What is it you want to do about that equation to pull out sigma t? You operate something, right? What is the name of the operator? Here's the equation. Here's the equation. And here's the c squared. I'm going to put some symbol in there indicating some sort of operation done both sides to pull out this one. ddt. Thank you. That's a differential operator. Let's differentiate this one. Right hand side is simple. What is it? 2 times c to the first? That 0 is correct. C is a constant, right? There's no t in it. So it's not 2 times c to the first. There's a 0 there. How about this one? How do you differentiate this one? What rule? Product rule. Dot product rule. Thank you. That sounds better. Yeah, dot product. Oh, there's what is written there. Okay. So see, put sigma prime t dt in there, right? Sigma t. Is that right? How about the other one? Sigma t, sigma prime t. Correct? Aren't they the same thing? So 2 times sigma prime t, sigma t, right? Equals 0. Well, you can get rid of the 2 in there. What does this mean? It means they are perpendicular, orthogonal to each other, right? As simple as that. But the next thing is harder to understand, and I'm going to apply this one to velocity vector. Suppose is it calls a corollary. Suppose is moving in constant speed like this. Isn't that what it means? Sigma prime t being constant, just like a circular motion. Or it could be something else, very different, but moving in a constant speed. And moving in a constant speed in the corner like that is very difficult. Can you imagine when you're running in a certain speed? When you're turning, you feel the force and how difficult it is, right? So you need extra force and work to keep the speed when you turn around. So it's very difficult to create constant motion whenever there's a hard curvature is in there. All right? But what we have proved up there is that sigma t, and it is derivative of this one vector function given, which is sigma double prime, right? Correct? Is always 0. Because it's just a formal object. You can start with the sigma prime t being constant, this length being constant. Then you can conclude, oh, next prime, sigma double prime t, must be perpendicular to each other. So this one is saying, if you move around like this path in a constant speed there, and there is a source of a force there creating this one, directly pulling like this, then it says if it's moving like this, where is the source of force? Perpendicular. Must be perpendicular. That's what it says. It must be down there, somewhere along that line. That source of force must be there to create this constant speed. If it is over here, where should be the source of the force? Must be here. So you can't just stay in there and keep pulling using different magnitude of force, make this one go in constant speed. You have to move it too, the source of the force. Whatever the magnet you have it there, you have to move around and follow that around to make it move in a constant speed, according to Newton, right? It has to be that direction. And this simple dot product calculation is very difficult to understand physically, why it had to be this hard to create this unit, the constant speed around this path. All right, I'll stop here.